gaseous substance, pardon me. And the behavior is independent of intermolecular forces again. That's what we're calling attractive or repulsive forces. So it's independent. We just deal with it as if all it does, all the physics, all the interaction you have in that gas has nothing to do with any intermolecular force. It can be completely described, of course, by the ideal gas law. So if it's an ideal gas, then PV is equals to nRT is sufficient to tell us almost everything about the gas. However, in reality, we don't usually have gases in ideal situation. However, like I said, the model, this ideal gas model, ideal gas law is sufficient for us to understand. And sometimes we just apply changes in the situation. We expect it to be this way, but okay, this situation has changed, and then we still see what we can do. So, an ideal gas law is used to predict the behavior of real gases under most conditions. That's why it's important. It's still useful. Under most conditions, it will work, it will not break. But in some few cases, we can adjust and still extrapolate our behavior of gas from the ideal behavior. So we have some limitation, and from now, by now, you should be thinking about limitations that you can have with this ideal gas equation. And the first one is that the ideal gas model, it provides a powerful approximation for many, but not all, of thermodynamic systems. And you will see where we begin to talk about specific types of systems and how even the first law of thermodynamics changes and things like that. So gases behave close to ideal when they're of high temperature. You need to note this. This is very important. So when the temperature is low, the behavior of the gas would deviate from what you call the ideal. When the pressure is also high, it will deviate from ideal gas behavior. So the ideal gas equation and the ideal gas interpretation works perfectly when the gas is of high temperature but low pressure. So limitation, if the temperature is low and the pressure is high, then it moves away from being ideal. Real gases deviate from ideal behavior, like I've said, at high pressure or low temperature. And when intermolecular forces become significant, one of our approximation of an ideal gas assumption of an ideal gas is that intermolecular forces are negligible, they are zero, they don't exist. But when you have a gas where the intermolecular forces that is between the particles become uh, significant, then such a gas deviates from the ideal behavior. And this gas, example, is when the gas is approaching condensation. And I believe we remember what condensation is and how we can relate condensation with temperature. So we know that if you have high temperature gas and it begins to cool, it can condense. So we need to relate things and put things together. So with low temperature, we're approaching condensation in such a gas, and that will certainly deviate from the behavior of an ideal gas. So those are some limitations. So we have talked about what ideal gases are, or when you talk about an ideal gas, what are the things you should think about? What are the characteristics of an ideal gas? We have talked about the ideal gas equation. I've talked about when they are useful. We have talked about the derivation of the ideal gas law. I've talked about when they are useful. We have also talked about limitation of this law. Okay, so let's go back to and refresh our memories again on kinetic theory. And we have used some of them today. We have talked about when temperature is high, what do we expect with the motion of the particles? They will move more freely. They will occupy more space. They will have more volume. So kinetic theory basically explains the behavior of gases by treating them as a large number of tiny particles moving randomly. Again, for kinetic theory, we link kinetic theory with microscopic behavior of gases. So you can take a container of gas, a cylinder of gas, but what is happening? And that cylinder of gas is a thermodynamic system. So what is happening with the gas? We know that the gas has molecules, is made up of tiny particles. And in this case, there are so many. We know that because atoms are in they are in millions, trillions, even in just one volume. When you are talking about one, we are talking about 1 meter cube. How many particles will you have in 1 meter cube? So, how many particles, how many particles or molecules of gas will you have in a cylinder? So when we cast our mind, when we talk about kinetic theory, we always talk about the microscopic behavior of that matter in question. And in this case, we're still saying let's use gas. So there are assumptions too when we talk about the kinetic theory, which is something that you must remember if you have forgotten. So we say a gas consists of huge number of molecules in constant random motion. Now you see the relationship with ideal. It says random constant motion. That's one of the assumptions for a gas to be ideal. What have we added for kinetic? The huge number of molecules. These molecules are point particles. You see another relationship again with our assumption with ideal gas. So you can see that the kinetic theory, ideal gas equation, they are quite related. So he said the molecules are point particles. So those particles are of negligible volume, not the system. Please note that. There's volume for the system, the container of the gas, there's space. However, what's the volume of the particles? These are large number of tiny particles that we're talking about. Say they are tiny, so their volumes are negligible. Again, for kinetic theory, there are no intermolecular forces acting. What we expect to have in that gas or in the behavior of the gas is that we have collision. And this collision, again, according to ideal gas, is perfectly elastic. So the gas pressure is caused by molecules hitting the container walls. That's what we have talked about earlier too. And the average kinetic energy depends on the absolute temperature. We have mentioned the absolute temperature with our ideal gas equation. So you see that the kinetic theory, and the ideal gas equation and law, they are together. If it's an ideal gas, it's going to behave in such a manner. Kinetic theory agrees with that manner very well. The only more or less contribution that it has brought here is the fact that you have large number of tiny particles, because ideal gas draws your mind to the microscopic form of the ideal gas equation, because we are dealing with the tiny particles and the interaction with them, not just what you have as a whole, which you eventually use. What's the temperature? What's the volume of the cylinder of the gas? What are the things that are happening within the gas? That's what kinetic theory takes you to. So, as I've said, that the kinetic theory, I'm seeing that the class is getting full now. Lateness is not allowed. This 8:35 is now that the class is holding. Preparation for virtual class for me is the same thing for physical class. So I take my physical classes as seriously as my virtual classes, and my virtual classes as seriously as my physical classes. And for me, attendance is a must. It's a must. Class reps, if you are here, you're going to give me the names of those who are in class, the attendance, and I'll tell you how many you are producing to me. So you will know what to do, whether you want to snap your attendance as you see it. So you pick your own classes or what, your own course mates, I don't know. But education, you will send your attendance. Uh, Geophysics, I guess it's only geophysics, or is it geoscience, whatever. You send your attendance, also physics. You will send me your attendance after the class. Mhm. So this one at the class is just filling up. Most of the things I've said, some of you have missed it. It's not new, but it's more or less like a refresher thing for you. Okay, so I've talked about ideal gas equation, and that kinetic theory is also a form of ideal gas, particularly in the microscopic form. So first of all, for us to get there, by kinetic theory, equation one is our ideal gas equation. Equation two gives us the pressure under the kinetic theory, how we can define the pressure of the gas. So this pressure, this is P, is given by 1/3 density of the gas, C square. And we are talking about the root mean square speed. Now you are talking about speed here. Here, density, you should remember, because we're relating pressure to density. And some of the things that we have talked about today, we have mentioned the issue of volume, we have talked about temperature. We have related temperature to kinetic theory, the kinetic energy, to the speed. So we see that speed is here, not too far from where we're coming. Because I'm not going into the derivation of this equation. You can do that, please, and get how this equation was derived. It will be good for you. However, I'm saying that we're not taking this pressure. This equation is not from the blues. We're talking about density. Density relates mass and volume. We know that. And then mass CV will give us the kinetic energy. And we know kinetic energy is related to the absolute temperature. So it's just some mathematics that brought us here. But this is a relationship for pressure under the kinetic theory, the density, and then the root mean square speed, which is your C square RMS. Okay? So going further from this equation, because what we want to do is I want to use the kinetic theory to get our ideal gas equation for microscopic particles, or in the microscopic form. So from that equation, we have PV. Initially, what we had was P is equals to 1/3 density. But our initial density is M over V. Is M over V. So that V is on this side now, just to show you that we are not, there's nothing new here. And this mass is the mass of just one molecule. So how many molecules do we have? What will be the total mass? Will be the number of molecules times the mass for one. We also know about this relationship still from kinetic theory. Is not what is new to us. So PV is equals to NKT. Initially what we had for PV was nRT. What we have changed here is that we have changed R to K. So K now is the Boltzmann constant, while R is the universal gas constant. But because here we're dealing with the microscopic one, we're talking about each mole of the gas and the total behavior we're considering the behavior of each mole, each molecule, to give us that microscopic behavior. So in this kinetic theory, is the microscopic PV is equals to nRT is the microscopic ideal equation. So in this case, this is another ideal gas equation, but in this case, you are dealing with the Boltzmann constant because you are in the microscopic level. So PV equation 4 gives us a relationship with PV, what PV can be. Equation 3 also does that. So what do? We can equate the two. You guys are not new to physics, so sometimes we just do things because of where we are going to, because of our area of interest. For us now, those who have worked on it, they have done other things. They knew what led them there. They say, okay, if this is this, then this can be this. If this is this, if this can be this. So if this is, if equation 3 holds, equation 4 holds, then we can equate the two of them by saying nkt can be equated to 1/3 nmc square, and that c is the root mean speed. So if we do that and equate them, we'll have this equation because we can cancel n. That's number of molecule is the same thing as number of molecule here. So we'll be having the mass of 1 mole. That's what this equation says. So from this equation, we have this. From that equation, you bring your m to the other side, and we are interested. Let me show you again. What we have here is 1/3. How did we get that half? We already know the relationship for kinetic energy, half mv squared. In this case, we are taking that energy of the average energy of the particles. So what do? And here is 1/3. What we want is half. So we take 3 to this side and divide both sides by half. And that's what gives us this equation. This equation is important. You can see that this is energy, is kinetic energy. So the molecular kinetic energy of the molecules that you have in that system can be equated to 3/2 kT. 3/2 kT. This is a constant, remember? Is Boltzmann's constant. So the kinetic energy can be given as 3/4 Boltzmann constant times your temperature. So the average kinetic energy of a gas depends on temperature. That's one thing we're saying in this equation. This is a constant. This is 3/2, which is 1.5. 1.5 of Boltzmann's constant times the temperature. Or we say that the energy, average kinetic energy of the gas molecules is directly proportional to temperature. Proportionality constant is 3/2 of Boltzmann's constant. These are things that you need to know and you need to remember. To derive it is possible. To also work with it is possible. Think of it, what are possible questions from what we have done actually now? What does this equation mean? What does this equation mean? One interpretation or inference from this equation is what we have said, that energy is directly proportionate for molecular kinetic energy is directly proportional to the temperature. It depends only on the temperature. Why are we saying only on the temperature? Temperature is a thermodynamic parameter. So this energy depends on this. We're not seeing volume nor pressure here anymore. So that's why the word only comes about. And not even the number of molecules. We're not seeing that here anymore. And so and we can see that it's directly proportional. So if the temperature is higher, then the energy will be higher. If kinetic energy is higher, we expect faster molecules. And if you have faster molecules, you have higher pressure. They will get to the container and interact with the container more. So there are different ways for which we can coin questions from this. The interpretation, the average molecular kinetic energy is dependent on how many thermodynamics parameter, or it depends on volume, temperature, and true or false, whatever you need to know. From the average kinetic energy, or from the average molecular kinetic energy, the higher the temperature, the higher the energy, the lower the temperature. The higher the energy, the lower the pressure. The higher the energy, the slower the molecules. You should be able to know uh, the right thing to say. So before I go into internal energy, which you have seen from first law of thermodynamics, I want to pause here and get questions. Yes, any questions, any confusion, any questions? Yes, I can hear you. Who is speaking? Michael Ajayi, Ikudeyinbu. You are the one who has been disturbing to record. Okay, I'm listening. Yes. So here for kinetic theory, we're dealing with the molecules. We're going to the microscopic level. Like I said, we're considering each particle. We're not just getting the container of the gas, the cylinder of the gas, and say what's the temperature. We're talking about the temperature or the energy that is being contributed by each particle. Each particle is our concern. And that's why the mass that you see, even in the kinetic energy, is the mass of one molecule. So we take them mole by mole, one molecule by molecule. That's what we call the mole. So in that state, we're using the Boltzmann constant and not, but there's a relationship between the Boltzmann constant and the universal gas constant. But we use the universal so that you don't make mistake. By the time you are using PV is equals to nRT, if that's sufficient to solve your problem, you will be using R and not K. And that R has a value. I think I even presented the 8 point whatever mole times whatever. And then the Boltzmann constant is also a constant. But we use that Boltzmann constant when we're dealing with microscopic level. Microscopic level is important for us. As we even go further in physics, we'll be talking about statistical physics and all that. That statistical physics that you are dealing with each particle, and it's a statistics, it is an average behavior. You may not be sure that all of them behave that way, but averagely, what do you get? And their contribution. So you are dealing with contribution of each particle. That's where you now use the Boltzmann constant and not the universal gas constant. Have I answered your question? It's like you are far from your mic, or you are using. I'm struggling. Go ahead. Yes, yes. The ideal gas. Yes. But as you go on, you are still going to see different processes that is different thing that may be applicable depending on what you are doing. Okay. Okay. So let's go on. Let's think about the internal energy. That internal energy, We'll be looking at it for different thermodynamic systems, and from our microscopic, that's the kinetic theory point of view. And then I think one or two, some systems relating it again to first law, because this is your internal energy is related to first law. Okay. So when we talk about internal energy, of course, in thermodynamics, it represents the total microscopic energy. You remember that? See, now we have talked about kinetic theory, and we are reminding ourselves with internal energy, which we have even seen in a larger picture, because first law is in a larger picture. But what brings about the behavior, the microscopic contribution, is that internal energy, the energy that is contributed by the kinetic energy of the particles and the potential energy of the particle, not what the environment is giving to the system. So it's an internal thing, internal energy. And so in a thermodynamic system is the total microscopic energy that is contained within the system, excluding the microscopic energy, whether it is kinetic or potential. The microscopic one come externally, maybe by the heat that is being induced, by the temperature of the environment, and things like that. So internal energy, as a reminder, that is what it is. So the total microscopic energy that is contained within the thermodynamic system. And when we say total, we know that our energy is usually in two forms, whether potential or kinetic. So internal energy is a state function. I believe you have done things like that when you say something is a state function. And what you mean is that it depends on the current state, not on the path. It's a state function. It's a function of which state it is. If it is in this state, then it will behave in a particular way. If the state changes, it will behave in a particular way. For example, if the thermodynamic system has higher temperature, there's a way it will behave. When the temperature cools, there's a way it will behave. So it does not depend, it does not care about the path. How did he get there? Where did he follow? Did he go from A to B, B to C? No. So a state function just is a matter of the state. That parameter is a matter of the state. And so an extensive is also an extensive property, which means that it depends on the amount of substance. So you have more substance, you should expect more internal energy and less, but of course, other things may determine that. But the more, it depends on the amount of substance. So we have two components, like I've said, of the internal energy, and that will be the kinetic internal energy and the potential internal energy. So energy, internal energy is a microscopic energy and is the total energy that that system has, which is contributed by the molecules or the particles of that system. We say is a state function, so it's independent on how it gets there. The value or the value of the internal energy depends on the nature of the state, how the state is at a particular time. Okay? So microscopic modes of internal energy. They have different modes. How do you get that internal energy? We said it's either going to be kinetic energy or potential energy, but we have different modes. Number one, translational kinetic energy. So this is the kinetic energy as a result of a straight line motion of particles. They are moving from one point to the other straight when you talk about the translational motion. So what is the internal energy? What is the kinetic energy that is generated according to that straight line motion of particle? That's what we call the translational kinetic energy, which is internal energy. This translational kinetic energy, this translational mode of internal energy is dominant in all gases. That's what you expect most. Okay. We also have what we call the rotational kinetic energy, the spinning of molecules. So though they are moving straight, they are still spinning. Some of them are spinning as they go. We can find this one in polyatomic gases. For some, is only if you are talking about monoatomic, that's the atom is just one, no molecules. Whatever, you still have that translational. But when the molecules becomes two, you will have translational, you will have rotational. You will see that. I think I'll explain it better. I explain it with a table somewhere. So there's a straight line contribution, straight line motion contribution to internal energy. There's a spinning motion contribution to the internal energy. There's also the vibrational contribution to the internal energy. So when you have oscillation, if oscillation occur, so now I've talked about straight line, I've talked about the spinning. If you also have oscillation occurring, that also gives a contribution to the internal kinetic energy. So if you have intermolecular, we also have, intermolecular potential energy. So forces can be between molecules. We have said for kinetic, we say it is negligible. And when we're dealing with ideal gas equation, it is negligible. However, sometimes we have them. And this internal potential energy could be as a result of, the van der Waals forces that, the hydrogen bonding, all those interaction that we know. But for ideal gas, we're downplaying them, but they do exist. And when we have them, maybe when a gas has deviated from the ideal gas behavior, this one become they become significant for us to recognize and also add its contribution to the total internal energy. This is significant. This our bonding is more significant when we talk about solid and liquids, and that should be clear in our minds. So intermolecular for gases, they are more spacious. The arrangement is, they are far away. So we say the bonding is negligible, and if it's a deep, they should be very, very far away. But when we're dealing with solid and liquid, intermolecular potential energy is important. Then we have the intramolecular potential energy, the energy that is within the chemical bonds. The chemical bond, we already have that when we are talking about one molecule. There's an interaction between one atom and the other. There's a bond. So that's the intramolecular contribution of potential energy. Okay, so it is good for us to know about the internal energy, the modes or the contributors, so to speak. So intermolecular modes. Now, when you are talking about the small contribution, and then phases, talk about phase change, and we'll see how that can be useful today and subsequently. So for ideal gases, the assumption is that the intermolecular forces are assumed to be zero. So these intermolecular forces for an ideal gas, what does that come to be? So the internal energy of an ideal gas, we know, depends on temperature. We have seen that when we're dealing with the kinetic energy earlier. So internal energy too for an ideal gas depends on temperature. So the internal energy is a function of the temperature for an ideal gas. Internal energy, ideal gas relationship. The internal energy is a function of temperature. So what do we say to that temperature and internal energy? How are they related? We said for an ideal gas, the internal energy is proportional to temperature. That should not be confusing to us because we have seen that at microscopic level, we can see that the energy is directly proportional to temperature. In this case, and here we said the molecular kinetic energy. So the internal energy is proportional to that. Uh-huh. So that's what we are saying here. And so When we have a rise in temperature, we expect to have an increase in internal energy. So the internal energy, now we use average kinetic energy, and we know that we're talking about the molecules. Again, we can interchange that with our internal molecule, and it can internal energy, pardon me, and it can be given as F over 2 nRT. You know what we got here in the formal equation was we had KT. KT. Again, Michael, I hope you are here with us now. But here we are dealing with the whole thing, the whole system. We have changed it to R. Now we are using N, NR. Uh-huh. So we have changed it to this N, number of moles. The other one you are also talking, well, is the same thing. It's the same N. But for our ideal gas, we're using this N. So what is this F? That's what we're introducing now. Saying that our internal energy is proportional or is a function of temperature. We have seen that one before, and that's not the problem. Relating our internal energy to this is also not a problem. However, I was saying that it came from, we saw how we derived it earlier. And then here I was saying we can even say it's a matter of F all over 2, where that our F is the degree of freedom for the molecules. And N is the number of moles, and your R is gas constant. So the internal energy per molecule, we have gone to one molecule now, is given as this. Again, Michael, you can see that this is for general. We have used R. When we're talking about one molecule now, we have come back to Boltzmann constant. So please know when to use the constant. What are you really talking about? So for one molecule, this is what the relationship we are going to have. But what is the degree of freedom of that one molecule? What's the degree of freedom? How far can it move? How far does it go through a translational motion? Does it oscillate? Does it spin? That's what this degree of freedom means. So the internal forces are significant in real gases, however, for liquid and solid. So if it's not liquid, if it's not your gas, your ideal gas for which you say the internal force just depends on temperature. If you are dealing with other gases, other real gases, liquid or solid, you'll be talking about the internal energy as a function of both temperature and volume. And for example, let's see the relationship when we're using the Van der Waals equation. You will see that the internal energy depends on the temperature, it depends on the volume, of course, the number of molecules, and heat capacity at constant volume also. So this is just an example to show that if we are dealing with an ideal gas, then that internal energy is a function of temperature. If it's not an ideal gas or liquid or whatever, it's a function of more than temperature. And in some cases, it's temperature and volume. That's what we try to show here. And here, the internal energy, and then we have introduced the issue of degree of freedom, which is coming from these modes, the different modes. Uh-huh. So what's the degree of freedom of a particular particle? Of the whole particle, total degree of freedom will give us the total internal energy of the system. But if it's per particle, then we will use this equation. I don't even know why I didn't number them. But we either use this equation or this equation. So this for total, this for a single molecule. And then, so phase changes are like what we have known. When a substance changes phase, we have talked about condensation today. So that's like a change in phase. And the more you add heat, as heat increases, the potential energy When a substance changes phase, heat added increases the potential energy by either breaking or stretching intermolecular bonds, while temperature remains constant. You remember latent heat? Uh-huh. So there's no change in temperature, but there's a phase change. It's moving from one form of matter to another, but the temperature is not showing because that added temperature is used, the added energy is used for the change in phase. So we talk about example of latent heat, latent energy, and that's the energy to change phase. And that phase, again, we're relating to intermolecular potential energy, intermolecular potential energy. So we can break the bond and then it moves freely, especially when we add heat. When we remove heat again, it can come together back to how it is. This just to bring phase change to what we are doing. And again, to talk about our internal energy. So degree of freedom and the internal energy. We have seen this equation. This equation, this for general, the general form of internal uh, energy. If we're dealing with a mole, a molecule, we'll be having our Boltzmann constant here. So if you have a monoatomic ideal gas, monoatomic, that's one atom, it's not biatomic, just one atom, ideal gas, you will have this equation. What does that mean? For a monoatomic ideal gas, the degree of freedom is 3. Is 3. So each molecule can store energy in different molecular modes, whether it's storing energy um, as a translational mode, rotational mode, or whatever mode. So each one can. So in this case, if you have monoatomic, the degree of freedom is 3. Okay? So let's look at the degree of freedom relative to the modes. For translational mode, the motion is in space and is along the XY direction, just like we know. And this XY direction translational motion is present in all gases. So for the translational mode, the degree of freedom is 3. And you can see that that's a bit common. We said it's uh, present in all gases. It's common because even from this, our relation and the equation we got before, you see that we're using 3. Even the one that we derived at this equation. So here now, this is the freedom, degree of freedom. And then, so we see that that's for translational mode. Okay, I think we're still doing well with time. That's for translational mode. And each contribution per molecule will give you this contribution to the internal energy. So the rotational mode, like if you have linear molecules, like oxygen or nitrogen, there's rotation. They rotate about 2 perpendicular axes. So because they rotate about 2 perpendicular axes, they have 2 degrees of freedom. They have 2 degrees of freedom. See 2 for this particular one. Yes. Then for vibrational mode, they behave like oscillators and they contribute both kinetic and potential. And we'll see when you get to this mode. So each vibrational mode will contribute kBT. This one now is 3/2. This one is giving you kB3. So it's higher in terms of contribution to this one. The vibrations become important only at higher temperatures because they require more energy. More energy is required for you to have this vibrational motion in with the particles or the molecules. So these occur when the temperature is higher. There's a condition for this one to occur. Even this one, the rotational one. And for electronic mode, we also have what we call electronic mode, which I'm not sure I showed in the earlier slide, is from electronic excitation. And it's also significant only at very high temperatures, very high, when you come to the level of plasmas and astrophysics. And you know, plasma, you get plasma at a very high temperature. So under our normal solid, liquid, and gas nature of matter, this does not exist. But we need to know that we can have this. This also at a high temperature, this one also needs more energy. And then you have the different degrees of freedom. Okay, so this is the table I was thinking about. So what's the total degrees of freedom that you can have in a system? Degree of freedom. And you know, we relate degree of freedom to the internal energy. So if you have the molecules in such a way that it is monoatomic, you will have that translational mode. And the translational mode will contribute to the internal energy. And because the degree of freedom is 3, the internal energy will be equals to this. So there won't be rotational for monoatomic molecule type. There's no rotational contribution, there's no vibrational. All you have is the translational for monoatomic, and the total mode, degree of freedom will be 3, while this will now be your total internal energy. If you have a diatomic molecular type, you are going to have translational. You are also going to have rotational because it's diatomic. And the degree of freedom for diatomic, like we shown here, is 2. Oh, pardon this, F is equals to 2 dot F is equal, is a mistake. It's F is equals to 2, and this F is equals to 3 is not there. So for the degree of freedom, contribution for translational mode will be 3, and that of contribution for rotational will be 2. And that's what we have here. So what's the total degree of freedom for diatomic? It will be 5. And you will have 5 over 2. Your total internal energy will now be 5 over 2 because the degree of freedom, F, is now 2 at low temperature. If it is at high temperature, the degree of freedom is going to change. At high temperature, you will have more. This is going to give you 3. This is going to give you 4 for rotation at high temperature. For the atomic molecule, is going to give you 4. So the total one at high temperature is going to be 7 all over 2. So for polyatomic arrangement, translational will give you 3, rotational will give you 3, vibrational will vary. Of course, it will vary according to temperature. So it can be there, it may be there, it may not be there. So at least you are going to have 6 degree of freedom, at least for a polyatomic molecule type. So polyatomic, meaning that more than 2 atoms coming together. So for such, you are going to have more than 6 degree of freedom. And your total here will be, your total internal energy will be at least 3 nRT, because this is 6 over 2 nRT. So the internal energy and first law of thermodynamics. So hitherto, we have talked about the internal energy. I've talked about what that internal energy is, and we have established the fact that you are talking about the energy of the molecules or the particles that constitutes your thermodynamic system. And we said it can be give different modes contribute to it. we know that, yeah, it's kinetic energy and potential energy, but the contributors could be the translational motion occurring in the molecules, rotational, vibrational, and the electronic interaction, or due to the potential energy that you have within the molecules or from one molecule to the other. We have also talked about the ideal gas. What was the total internal energy? I would say that total internal energy is the microscopic kinetic energy that we got before, but is as a result of the different modes as a result, and those modes contribute to what we call the degree of freedom. We saw the internal energy of the system and of each molecule. Okay, we went on to talk about for real gases, the internal energy does not only depend, is not only a function of temperature, but it can be a function of other things. And the internal energy, particularly the intermolecular potential energy, is related to what we call, what we know as phase changes or the latent energy that we have always known. And the degree of freedom depends on the type of molecules, whether they are atomic, they are monoatomic, polyatomic, or diatomic. So those are basically what we have said here. So relating it to our first law, that one, anybody in this class at this point should be able to say that. So we can have the first law, our internal energy relationship, to be equals to Q plus W. When you have that, please don't confuse it. I prefer to use universally this one. Change in internal energy is the difference between the heat that is being absorbed by the system and the work that is being done by the system. For me, that's easier to visualize. A thermodynamic system is a system for which you use heat to do work. How do you get the heat comes into the system and you want to use it to do work? So I always like this one. Absorb heat, so the difference between what you gave that system and the work that is being done is the change that you have in internal energy. Note that this is not internal energy. If you put this as internal energy, you will be wrong, because we have explained the fact that internal energy is not coming from anything but the behavior of the molecules inside. However, that energy they have can be affected, can change as a result of absorbed heat and what is being taken out. So you need to understand this. But why did I put this one? It was the first one I put, and I said no, so that we can clear it. In some text, when you are reading, you can have this. Note that whenever you have this plus here, it means that you have a negative work. So negative work, and then but the original one is this one, is this equation. How do you have negative work when work is being done on the system? Is a negative work, because for a thermodynamic system, we want to use that system to do work. Is to help us. We should not be helping the system again. So that's a negative work when work is being done on the system. However, if work is being done by the system, what we expect, then this equation, it will be a positive work, and this equation we hold rather. So first law gives us relationship between absorbed heat, the work that is being done by the system or on the system, and the change in internal energy. So actually, this should even read the first law of that thermodynamics and change in internal energy. Okay. So before I talk about different processes of an ideal gas, I'm using our understanding of internal energy, our ideal gas, our kinetic theory where necessary. I want to pause to take necessary questions at this point. Yes, Ikudeyinbo. I didn't hear that. Yes. Okay. I think that's a good question to ask. It shows that you are thinking. For entropy, we will relate entropy first of all with maybe our collision, because it tells us about disorderliness, and later we extend entropy with our second law. You people have done first and second law, I want to believe. Have you? Uh-huh. So you want to, relate it with that, relate it with energy, because when you talk about second law, you talk about your heat system, your thermodynamic system. That's the heat engine, and then you talk about the refrigerator and how you can relate them. But our basic understanding of entropy will talk about how orderly it is, and in terms of or the motion, collision, and randomness. In a way, it is related because you are dealing with motion. You are dealing with motion. But this one is so that entropy, if it increases, if the entropy in the system increases, and you have more, let's say, rotational behavior in that system, then your degree of freedom is going to, or you now have rotational or motion because of the increase of the entropy. Yes, we can find a way of relating them. However, you know that these our modes of um, modes of internal energy is as a result of possible motion that you can have in that system, which is not only dependent on how random it is. By the way, from ideal gas, kinetic theory, and even from what we should expect, the system has a lot of particles and they are constantly in random motion. But like we said, for vibrational, for us to have that occur, we think of higher temperature. So it's not just what do you call it now? It's not just the entropy, because the entropy is there. But is it monatomic? Is it diatomic? So what we're trying to say is that what contributes to the internal energy is this mode of motion. I don't know if you get me. Is yes, yes, yes. And the degree of freedom we are given condition. In fact, the one that we are more at home with and which you will use often is that degree of freedom of 3. Because when you're talking about the average internal energy, that average kinetic energy that we derived as 3 over 2 kT, that's the average internal energy. You are still dealing with internal energy. You are dealing with internal, and you have used 3 as degree of freedom. So if you understand, so we're using that translational one more. Okay. Question. Any other questions? Any other question? Okay. Thermodynamic processes for an ideal state of our ideal gas. We want to look at a few and how they behave and how we can solve problems when we're talking about such processes. I believe, how many processes have you people done before now? Because you should have seen different types of thermodynamics processes. Ifeanyi, unmute and tell me the ones you know. Ezionye, Ifeanyi, unmute. If I call your name, you don't answer me, that means you are not in class. So class rep, you will note names that I'm removing. Ezionye, Ifeanyi, unmute and speak.
Morning, ma.
Morning, sir. Thermodynamic processes that you know.
Oh, okay, ma. Ma, we did isothermal process,
Okay.
isobaric process.
Okay.
It's,
That's the two you can say. So you must have done all the processes that I want to mention. I just wanted to know whether you have done them or not. Okay? But
ma.
as a matter of completion for the area I wanted to speak to today and to
Yes.
just relate first law and internal energy, I will still go on. Okay. So when you talk about isothermal process, you know what an isothermal process is. And this diagram is a PV diagram, and it's a very common diagram when we're dealing with work done, because we know that work has been given as the integral of what? How did you define work done before? Onuoha, Eberechi, or mute and speak. I won't call you twice. If I call you, you don't answer me. You are not in my class for today. Onua, Eberechi.
Morning, ma.
Morning, ma. Yeah. So what's the relationship for work done, particularly using our PV diagram? Work done. What's the relationship that we have for work done? Or tell me anyone you know for work done. What's your department, Eberi?
Geophysics, ma.
Uh-huh. So you're at home with physics. So work
Yes.
done. Yes, tell me work done. You can leave. Okay, go ahead.
Ma?
Go ahead.
The work done is equal to the area under the curve. That's the question.
What's the area under the curve? What's the area under the curve? Emmanuel Adesanya. I didn't tell you to mute because you have not said anything.
Sorry, ma.
I didn't tell you to mute. Emmanuel Adesanya.
Good morning, ma.
Morning, sir.
Yes, sir.
One relationship that we have for work done.
I know there is one formula that relates work done with pressure when integrating the pressure with dV.
Yeah. PDV. You should be
Yes, ma.
confident at this level. Have you guys had any tests? I know how you can mute.
No, ma.
You have not had any tests because
Yes, ma.
by now all those ones should be at your fingertips. Okay. So I said this PV diagram is important. The area under the curve can be taken, but how will you get the area under the curve? Often. So you can show the area. Work done is equals to PDV. You should have it here. You should have it in your hand. Sometimes you take the integral, sometimes in question, you already have volume 1, volume 2. So you can tell us the change in volume and pressure is given. Work done. You don't have much problem. So this equation that we have here is the equation of an ideal gas. PV is equals to nRT, still holds. For this particular PV diagram, we have our VA here and then VB here. So the volume started from this point and then came to this point. Our pressure for A was this, and then here we also have change in pressure. So pressure is changing, volume is also changing. Let me ask Dixon, how is pressure changing here? From VA to VB, is it increasing or decreasing? Christian Dixon, over to you. How is pressure increasing? I said I won't call you twice, so you will just remove your name for me. Christian Dixon. So I don't want to see his name in attendance today. His name is very easy for me to remember. Christian Dixon, go in. Christian Dixon, gone. Ifeoluwa Adegbite. How is pressure changing here? Ifeoluwa.
The pressure decreases. It's decreasing now.
It's decreasing. What about volume?
There's an increase. There's an increase in volume.
There's an increase. I didn't hear you well. What's the volume? How is the volume changing? Ifeoluwa, we are waiting for you. How is the volume changing?
Not sure.
You are not sure. Why are you not sure? You should be sure. So you hold on until you get the answer. Christian, why are you raising your hand? I said on mute.
Sorry, ma. I was trying to unmute.
You don't know how to unmute, my brother.
I'm sorry, ma.
So how is he has told you that pressure is decreasing? Do you agree with him?
Pressure?
Yes, sir. Pressure
from A to B is decreasing. Then the volume is also decreasing too, I guess.
Why are you guessing? You are showing you from diagram. You are guessing. You are not supposed to guess. Ayomide Otusanwo. I say I don't want to call you twice.
Yes, ma'am.
Okay. So what's happening to the volume?
The volume is increasing, ma'am.
Why?
Because from A to B, it's actually increased. It's increasing.
Thank you very much. Adegbite, did you hear that?
Yes, ma'am.
And Dixon, did you get that?
Yes, ma'am.
This is easy to see. This is our normal graph. This is 0. We're saying this arrow already shows you that you are increasing upwards. So this will be 0. This can be 2, 4, 6, 8, your normal graph. And in this case, this 0 is also increasing this way. So this can be 2, 4, 6, 8, 10, 12. So it's also increasing. From here, you will see. You don't even need this colored place to know. And for your pressure, see the first one. And for the second one, see the second one. So usually this one, we use it for what? Our work done. It's easy for us to do our work done with it. And we know the pressure at a particular point, and then we look at the change in volume. So for an isothermal process, like temperature remains constant. And if temperature remains constant, this equation can also help us, like from Boyle's law, if you remember Boyle's law. So this PV is constant, and your temperature is also constant. So what else can we see in an isothermal process? For an isothermal process, we know that for all of our processes, this equation is easy for us to remember. That work done is equals to the integral of P dV. And an ideal gas equation tells us that PV is equals to nRT. If you did all this system, you must have done this part. But I'm still going to add it for completion in case you never got it the first time. So P, what is pressure? We're looking for work done. If we are to look for work done, what will happen? And why are we looking for work done? First law, we want to relate it to our different thermodynamic processes. And there is work done in our first law. So how can we obtain our work done in such a system? PdV is an ideal gas. Is an ideal gas. So we use the ideal gas equation to get our P, to get what our relationship for our pressure. So if we do that, our P will be equals to nRT all over V. And then to put it back into equation 5, we will have work done is equals to integral of nRT V dV. nRT, all these are constants. From our simple integration, we'll bring this nRT out. And then we integrate. What are we left with now? 1 over V dV. That's what we are left with, 1 over V dV. What are our boundaries? Is that where are we moving from? We're moving from volume A to volume B. So what do? We get the integral of 1 over V dV, which is ln V. But because we are moving from VA to VB, it will normal thing will be saying VB minus VA. But because it is integral, it's now ln VB all over VA. If you cannot remember or you never did further maths and you are still in 200 level, you don't know how to integrate basic things, please go and learn. You don't know how to differentiate, go and learn. Because we'll be borrowing as if everybody knows, but it's not difficult. If you have not seen it before, 5-minute video, you'll be good, my brothers and sisters. So what we now get as our work done? Our work done is now nRT ln VB all over A for general system. What does this mean? This means that our work done will be positive if our VB is greater than VA. W will be positive. But if VB is less, sorry, I wrote VB, VA. If VB is less than VA, then your work done, this thing will become negative. It is positive if VB is higher. That's if VB is higher, that means when you have increase in volume. When the volume is increasing, the work done is positive. And when the volume is decreasing, the work done is negative. So, but we are talking about specifically for an isothermal system. So what do we get? So recall that your first, from your internal energy depends only on temperature for an ideal gas. So for an isothermal process where temperature is constant, that means internal energy will also be constant. Interpretation of isothermal process in terms of internal energy. Temperature is constant. Internal energy depends on temperature. That means internal energy will also be constant. And if it is constant, what does our first law become? First law is that Q minus W will give us our change in internal energy. So Q will be equals to W because our internal energy is constant. That means it is not changing. So internal energy is not changing because temperature is constant. So for an isothermal process, our absorbed heat energy is equals to work done. Meaning, again, in another way of saying it is that all the heat that is being supplied to that system is used for work for an isothermal system. Okay. What about an adiabatic system? In an adiabatic system, there's no exchange of heat between that system and the surrounding. So it's not absorbing heat. There's no Q. Q that is coming there is equals to 0. Again, work done, is PdV. But for an isothermal adiabatic process, we also use this equation. You must have seen this also. For an adiabatic process, PV raised to power gamma is a constant. So what is our P? Again, our P becomes K all over V raised to power gamma. If we put that as our P and dV, we'll be getting this as our work done. So we know how to get the work done for an adiabatic process. We have seen the one for an isothermal, and we have seen what first law becomes. So for an isothermal process, this is our work done. W is equals to nRT ln V2 all over V1 or VB all over VA. And then we have seen that our first law becomes this. Again, for an adiabatic process, we said coming from this equation is the equation we're using for an adiabatic one. And the work done is given as this. So by first law for an adiabatic process, we ought to have Q minus W is equals to DU. But our Q is 0, meaning our change in work done is equals to, and our change in internal energy is the negative of work done. Or we say change in energy is the same thing as the work done on the system. Or change in energy is the negative of the work done by the system. So please, you need to get this right. If work done is negative, that's if this is negative, just W is negative, meaning that DU will be positive. And if DU is positive, it means that internal energy is increasing. I will take that again. If work done, that's W, not minus W. This minus is coming from our normal first law, which is Q minus W will be equals to DU. Or DU is equals to Q minus W. But in this case, our Q is equals to 0. So we have that minus W. But if the work done is negative, meaning if work is being done on the system, the DU, what we'll have here is that DU will become positive W. And if that is the case, that means our internal energy will be increasing. However, if our W is positive, that if work is being done by that system, then we're going to have DU will be equals to minus W. And what does that mean? Is that the internal energy is decreasing, which we can picture. Now this system is working, but there's no heat that is given to it. So what heat will it be using to do work? If you will do work, then it will be using part of its internal energy. So if work will be done by the system, meaning that W will be minus W, meaning that W will be W. If work will be done by the system, W will be positive. But this system is adiabatic. There's no heat added. So change in internal energy, it will decrease in internal energy for it to do work. Energy is neither created nor destroyed. So if work must be done, energy must be used. And energy has not been added. Definitely it will use its internal energy. And that means that for work to be done by the system and this equation will hold, then the internal energy will decrease. For the internal energy to be equals to plus W, it means that the internal energy is increasing. For that to happen, work will be done on the system. I believe that is taken. For an isochoric process, here volume is constant. For isochoric process, volume is constant. If volume is constant, what it means is that there's no change in volume. Our work done is W is equals to PdV. That means dV is equals to 0. And what means is that work done will be equals to 0 for an isochoric process because there's no change in volume. So work done will be equals to 0. And there's no change in volume because the volume is constant. So the V is equals to 0. It's not V that is equals to 0 for an isochoric process. V is not 0. It is change in volume that is 0 because volume is constant. So if that is the case, our W will be equals to 0, meaning that our absorbed heat will be equals to the change in internal energy. So if that system absorbs heat, it will only be accounted for in the change in internal energy. It will not do any work because the volume of that system is constant. Okay, for isobaric process, is the pressure that is constant. And if the pressure is constant, we're okay with that. PdV, we'll just get that constant P and we'll be able to get our work done. So in this case, the volume increases, and if volume increases, then the work done is positive, meaning that dV will be positive if volume increases. If volume decreases, then the work will be negative. And when work is negative, what it means is that work is being done on the system. So by first law, and in an isobaric process, while pressure is constant, we will have our Q to be equals to PdV plus du, or we can say Q minus work done is equals to du, and Q minus work done is equals to du, or we say W is equals to PdV. And we said this can be positive or negative. So for an isobaric process, we don't have problem. What about our cyclic process? For a cyclic process, the final state of the system is the initial state. So where this state started from is where it ended in. So for such a state, the change in internal energy will be equals to 0, because we mentioned that the internal energy is a state function. So if it was A at point 1 and B at point 2, if it eventually comes back to point 1, U1 will be equals to U2. So for a cyclic process, what is constant is the internal energy. It's not that the internal energy is zero, it is constant. So there's no change in internal energy. So what it means is that our Q minus W will be equals to zero. And so Q will be equals to W. So all the work, the absorbed heat will be used to do work. And so we see Q is equals to W, all of the work. There's no change in internal energy, just in the case of isothermal process. For isothermal process, we said that internal energy depends on temperature. Temperature is constant, so internal energy will be constant. For a cyclic process, initial internal energy will be equals to final internal energy. So change in internal energy is zero, and so it will be constant. Okay, I think this is where we draw the curtain today and we end the class. Any questions? So at the end of the class, I'm having 46 students in the class. So class reps, please, I will have attendance for 46. If you want to screenshot, you can. Pick your own and send me. Just make sure if it does not tally to 46, okay, I'm seeing 48, 46, so I may take 47. I want to assume somebody is having network problem. I'm just being very lenient today. So I can take 47. Class rep physics, are you here? On mute, let me know you are in class.
Yes, ma'am.
Uh-huh. Adebukola Michael. Michael, plenty for this class. Okay. Geophysics, class rep. Class rep physics, geophysics.
Good morning, ma'am.
Good morning. So to confirm that, I'm going to have attendance from you. Education, class rep. Education. Or are they not taking this course anymore? Somebody answered that is from education. Anyone from education? I thought somebody said it was from education earlier today. Physics, have they been coming?
Yes, ma'am.
So why